Okay, wonderful. Welcome to the second lesson of electric circuits. Today we're going to be covering some very important topics. We're going to be covering Kirchoffs laws, dependent sources, an example of dependent sources as covered in the last lesson, and we're going to do resistances in series and parallel and their simplifications. So let us begin. We start with KCL, which is Kirchoffs Current Law. So, Kirchoffs Current Law states that the algebraic sum of all currents in any node in a circuit equals 0. So what exactly does this mean? Let's define a node with 3 resistors. R1, R2, and R3. We'll see later in later lessons that this is a Y circuit. So let's define V1 and we define V2 as well as V3, and we define the currents in the usual passive convention sign sense of flowing into the positive terminal. So now what Kirchoffs current law says is that the sum of all the currents, so this current flowing into this node, this current flowing into the node, and this current flowing into the node, all equal 0. So I1 plus I2 plus I3 equals 0. If we had to have defined I2, I2 flowing out of the circuit, obviously we would change the orientation of V2, but then we would define I1 plus I3 minus I2 equals 0. So that would be current I1 and I2 flowing into the node is equal to the current flowing out of the node I2. Wonderful. As simple as that. KVL now is Kirchoffs Voltage Law. It is quite analogous to Kirchoffs Current Law, except now we say that the sum of all voltages in a loop or a closed loop or a closed path in a circuit equals 0. So the sum of all voltages around any closed path, which is a loop in a circuit, equals 0. So what does this mean? Let's define a loop in a circuit, 2 resistors and a voltage source. So we have voltage Vs and we have another voltage V1 and another voltage V2, and this is R1, R2, and obviously currents flowing in this direction, Is. So this is the current flowing out of Vs. So Kirchoffs voltage law says that Vs, this voltage, minus V1 minus V2 equals 0. So this voltage is equal to the sum of this voltage and this voltage. So the algebraic sum of all voltages around any closed path in a circuit equals 0. Noting that the voltage orientation for Vs is opposite to these voltages. This is why the negative sign comes in. We can similarly, just to explain it a bit better, we write it like this. So this voltage, the voltage supplied to the circuit, is equal to the voltage utilized by these 2 resistors. Now, let's do a simple example to describe how we can utilize KCL and KVL within a circuit. Let's define this circuit such here we're going to utilize two sources. And often within circuit theory, circuits may at first appear to be very daunting or confusing, but a simple application of the basic laws is often more than adequate enough to solve these. So now let's ask ourselves, what do we want here? What is the unknowns? So we do not know what I alpha is, and we do not know what the voltage drop over the 50 ohm resistor is. So let's work it out. Let's use KVL. Well, we could also note that we don't know the voltage drop over the 10 ohm resistor. So 120 volts, this is essentially Vs from this circuit, correct? So we define this loop with the voltage source, the 10 ohm resistor, and the 50 ohm resistor. This is a closed loop within the circuit. We say 120 minus voltage of alpha, so we define plus minus voltage alpha minus the voltage of the 50 ohm resistor equals 0. And similarly, we can use KCL, the sum of all currents in any node equals 0. So we use this node here, and we know that I alpha plus 6 amps, which is the source supplying in here, plus I of the 50 ohm resistor, so this is the current flowing through this 50 ohm resistor, equals 0. Wonderful. This is essentially, a mistake, I alpha. So we define I alpha. Going into this node, we know that the 6 amp also flows into this node, and then we assume that this current I of 50 is flowing out of the node, plus I of 50, or it's equal to I of 50. So we have the I alpha flowing into the node, 6 amps flowing into the node, and I of 50 flowing out of the node. So the sum of those two must equal the current flowing out of the node. Wonderful. And now we can also use Ohm's law, which is, as previously described, R equals V over I. Now let's substitute into this first equation 120 minus V alpha, so V equals R times I, so we know that this is 10 ohms times I alpha minus, so V of 50, we know that that is as well R times I, and here we know that I of 50 is I alpha plus 6, so we can say I alpha plus 6 times it by the 50 ohm, so this is I of 50, as we figured out in equation 2 through KCL, is this value, and then we have 50, which is the resistance value, equals 0. From there, we can do some simple algebra. So we have 120 minus 300 equals 10 I alpha plus 50 I alpha, and then we get I alpha to be negative 3 amps. Wonderful. So essentially what is happening here is that this I alpha has yet again been defined in the incorrect direction and is in fact flowing this way through the circuit, which might seem a little confusing, but is in fact true. So let's work out what the I of the 50 ohm resistor is. So this is the current flowing down through this resistor. We have I50 is I alpha plus 6. So we have negative 3 plus 6 is 3 amps. So we have 6 amps flowing in here, 3 flowing down, and 3 flowing that way. Even though this 120 volt voltage source seems that we would define the current flowing out, it would in fact be flowing the other way. Okay, now we are going to do a dependent source example. Dependent sources initially seem quite tricky, but however, like I said earlier, if you apply the basic concepts and equations, they seem to sort themselves out. So let's utilize this circuit example. Throughout this course I'm going to be doing various examples. You're more than welcome to pause the video once the circuit has been drawn and to attempt it on your own. Otherwise, there are various examples with answers given in Nielsen and Riedel. Alright, I hope that's all clear. So we have a 10 volt source, we have a current IS, we have a loop I1, we have a 6 ohm resistor, we have a current dependent voltage source. So this voltage is a scalar multiple of 3 times the current flowing through this circuit. Then we have a 2 ohm resistor as well as a 3 ohm resistor, and we define a voltage VO over this 3 ohm resistor. So now we want to know what IS is and what I out is, or IO at least. So let's first use KVL. So Kirchoffs Voltage Law at loop 1. So this is loop 1. So we know that the 10 volt source must equal, so the voltage, the algebraic sum of any voltages within a loop is equal to 0. So this voltage must equal this voltage. So we have 10 is equal to the voltage V over 6 ohms. And from Ohm's law, we can say that V of the 6 ohms is 6 ohms times IS. So the resistance times the current. Then we can get IS as 10 over 6 amps. We can leave that in fraction form for now, as it might simplify later. So now we have IS. We would like to know what I out is. So we use KVL again, except this time at loop 2. So we have 3 times IS, which is the voltage source, is equal to the voltage of the 2 ohms plus V out. Wonderful. Now we know that 3 times IS is V2 plus VO. V2 we can substitute Ohm's law, so we have I out times 2 as well as V out, which is 3 ohms times I0. So then we have 3 times I of S, which is 10 over 6, and then 5 times I0. And I0 simplifies to 1 amp. Then we can calculate V out simply as R times I, so it's 3 ohms times I out, which is 1, so simply get 3 volts. And it's as simple as that.